There is one last trend for us to discuss, and it's a trend that involves performing multiple successive ionizations. So we've previously talked about the first ionization energy, the energy required to remove the first electron, but what if we wanted to remove a second electron? That would involve the second ionization energy, so going from the +1 to +2 oxidation state. We'll consider magnesium here. So the first ionization is going from magnesium to Mg++ plus an electron. And you can do this in a lab and determine experimentally that the first ionization energy for magnesium is 735 kilojoules per mole. Let's now talk about the second ionization energy, when you go from Mg+ to Mg2+. Let's predict what the second ionization energy would be for magnesium. Do you think it's going to be greater than, less than, or equal to the first ionization energy? Take a moment to think about this and put in your answer. All right. It turns out that the second ionization energy for magnesium is going to be greater than the first ionization energy. And here's why. After having already removed an electron from the magnesium to make Mg+, you now have a positively charged ion, and it's going to be hard to rip away a negative charge from that, right? Opposites attract, and so that electron is going to be even more tightly held to the magnesium now because you have an Mg+ ion, and so again, it's going to be harder to take away that second electron. Let's think of an analogy to get an idea of this, right? So we'll take ourselves out of the world of chemistry for a moment and use an analogy for this. Instead of thinking about electrons, let's think about money. Let's say that my friend comes up to me today and says, "Hey Scott, can you loan me $20? And I give my friend the $20 as a loan. Think of that $20 as being like the electron that I'm losing, right? As I give my friend the $20. And I'm going to be a little bit annoyed when my friend asks me to do that. That's what the ionization energy represents, is like my level of annoyance with my friend. I'll be a little bit annoyed, but, I'm willing to do it because I'm a good guy. Now, let's say that my friend has not paid me back, right? So I haven't gotten that electron back. I haven't gotten the money back. And the friend comes back to me again the next day and says, "Hey, Scott, can you loan me another $20? Now I'm going to be a little bit more annoyed, right? I'm going to be a lot less likely to loan him the money the second time around because I haven't been paid back yet. My level of annoyance will be much higher. And similarly, it will be harder to remove the second electron from the magnesium. The second ionization energy for magnesium goes up to 1,445 kilojoules per mole. It doubles. It's much harder to remove the second electron. Now let's say that my friend still hasn't paid me back and comes back again on a third day and asks to borrow $20, right? That's like the third ionization energy. I'm going to start to get really angry at that point, right? I'm going to be even more annoyed with my friend now. And likewise, the magnesium is going to be much less likely to lose another electron. And so now the ionization energy jumps to 7,730 kilojoules per mole, just like how my level of annoyance would probably jump up by about 5 times. I'll probably still do it because I don't really have any friends and I want to try to maintain as many friends as I can, but I'm going to be really annoyed about it. So what we see here is that each successive ionization energy will be higher than the last. Every ionization energy will increase compared to the previous one. But let's see why it is that IE3 is so much bigger than IE2. Why is it being multiplied by 5, right? Whereas when you go from IE1 to IE2, it's only multiplied by 2. Why does it go up by a factor of 5 here? To understand this, we can write out the electron configurations for all of these species that we have here. For the magnesium, we have neon 3s2. And then for Mg+, we've removed an electron, so that's going to be neon 3s1. And then for Mg2+, we would remove another electron, so that's neon, just neon, right? So what we're noticing here is that in these first two ionizations, you are removing the valence electrons, right? Because magnesium has 2 valence electrons. So you remove the first one here, and then you remove the second one there. You're taking away valence electrons, which are further away from the nucleus, and they're not very tightly bound to the nucleus. But when you do the third ionization step, you have to now crack into the core. You're going to have to go into the core electrons and break it up to go from the configuration of neon to a configuration of helium 2s2 2p5. So the third electron is a core electron, which is much more tightly bound to the nucleus. It's much closer to the nucleus, and it's much harder to remove. And that's why the third ionization event is so much higher in energy, why you have to put in so much more energy to make it happen. to go back to our analogy with like my deadbeat friend who doesn't pay me back on his loans, like think about the valence electrons as being like cash that I have in my pocket. So let's say that I have $40 in cash in my pocket. The first day, my friend borrows $20, doesn't pay me back. The second day, borrows the other $20. And now I don't have any more cash in my pocket. So when my friend comes back on the third day and asks to borrow another $20 from me, I have to go like to the bank and go to the ATM and take $20 out to loan to my friend, right? Taking it out of the bank is now like cracking into the core electrons. And then that's when you get like really pissed, right? Because now you have to really start going out of your way to help your friend out. And right, that's where your level of annoyance goes way up. The ionization energy likewise also goes way up. So you can learn a couple of things from seeing the energies of multiple ionization events. One thing that you should always keep in mind is that each ionization will be more difficult than the last. And additionally, whenever you see a big jump in the ionization, like what we saw right here, when it multiplies by 5 times, a big jump in the ionization indicates that you've exhausted the valence electrons and now you've started dipping into the core. You've noticed from seeing this trend here that magnesium has to have 2 valence electrons because the first 2 are relatively easy to remove. The third one is really hard to remove. That's how you know that magnesium has 2 valence electrons, or it's another way that you can determine it. That brings us to the end of chapter 12. So you could take a look at these slides to see the concepts that we've discussed in this chapter. We talked about a lot of stuff in chapter 12. It's a long chapter, so there's 2 slides here that you can refer to and use to study. And up next, we're going to start chapter 13.